I want to tell you about a box. It sits outside, it doesn't move, it has no fuel tank, no solar panels, no wind turbine, no connection to the grid. You feed it your organic waste, food scraps, kitchen garbage, brewery runoff, the stuff you throw away every single day, and it quietly, continuously generates electricity. Around the clock, without stopping. Inside that box are living organisms, bacteria. Specifically, a class of microbes called exoelectrogens, microbes that literally breathe electricity. They consume organic waste and in the process exhale electrons. Those electrons flow through electrodes, generate current, and produce usable energy from material you were going to throw in the bin anyway. This is not science fiction. This is not a concept paper or a university lab experiment that never made it out of the building. This technology was funded by NASA, developed with contracts from Johnson Space Center and Ames Research Center, validated in real industrial installations, and it is operating right now at breweries and food production facilities across the United States, turning waste streams into energy with no combustion, no solar input, no moving parts, and no fuel cost. The reason you've never heard of it has nothing to do with whether it works. It works extraordinarily well. It has everything to do with the fact that it runs on garbage. And there is no business model in selling you fuel made of your own trash. Before I break down exactly how this works and what it means for backyard and small-scale energy generation, hit that like button and subscribe to Lost Tech Vault right now. Every video on this channel connects to the next one. Let's start at the beginning, because the NASA connection here is not a marketing hook. It is not a loose association between a product and the space agency's name slapped on a label for credibility. It is a documented, published, peer-reviewed origin story that starts at MIT and runs directly through two separate NASA research programs. In 2006, a group of graduate students at the Massachusetts Institute of Technology founded a company called Intact Labs, later renamed Cambrian Innovation, using funding from a NASA Innovative Advanced Concepts grant. The grant was awarded to study what NASA called bioelectric space exploration. The core question NASA was trying to answer was straightforward and profound. In a closed spacecraft environment with no supply chain, no resupply missions, and finite resources, how do you turn human waste into something useful? The answer they found was exoelectrogenic bacteria. These are microbes that can, in the absence of oxygen, transfer an electric charge to a metal outside the cell membrane, essentially breathing by exhaling electrons rather than carbon dioxide. The first well-studied example, Shionella onidensis, was discovered in 1988. Since then, scientists have identified an entire class of similar microbes, capable of either exhaling or inhaling electrons, and in some cases doing both. NASA saw the potential immediately. In 2011, NASA's Ames Research Center oversaw an SBIR contract with Cambrian Innovation to develop a life support system that would use exoelectrogenic microbes to extract carbon dioxide from spacecraft air while generating oxygen, water, and methane. The following year, Cambrian worked on another SBIR contract with Johnson Space Center to build a reactor that could treat wastewater while functioning as either a microbial fuel cell, converting waste directly to energy, or a microbial electrolysis cell, using a small electrical input to break down waste and produce useful hydrogen or methane. That Johnson Space Center contract produced a patent. It produced a working cell, it produced test data, and it produced the foundation for a commercial product that Cambrian announced in 2013 and has been selling ever since. The product is called the EcoVolt Reactor. Here is how it works at the level that matters for understanding what this technology actually does. The system applies a small electrical charge to enable what Cambrian's founder Matt Silver calls biologically assisted electrolysis. Microbes on the anode break down organic waste to generate electricity, while different microbes on the cathode, electromethaноgens, feed on that electricity as well as carbon dioxide to create methane-rich natural gas that can be burned for power. The gas provides significantly more energy than the charge put into the unit, making it a net positive energy generator. Read that again slowly. You put in a small electrical charge, you get back more energy than you put in. The difference is supplied by the bacteria consuming organic waste. The system is not violating thermodynamics. It's harvesting chemical energy stored in organic material that would otherwise decompose anyway, releasing nothing useful. The bacteria are the engine, the waste is the fuel, the output is electricity and methane. The natural gas the EcoVolt produces is 70 to 80% methane, higher purity than most alternative biogas systems achieve. And because the system is prefabricated and modular, it can be transported by road, is straightforward to set up, and can scale by simply adding another unit if a facility expands now. The industrial-scale version of this technology sits in a shipping container and is designed for breweries and wineries generating thousands of gallons of wastewater daily. One of Cambrian's brewery customers uses 2 EcoVolt reactors to generate up to 95 kilowatts of electricity, allowing the brewery to eliminate over 4,000 metric tons of carbon dioxide emissions per year through energy savings. That's the commercial application. Here's why it matters for you. The underlying biology, exoelectrogenic microbes consuming organic waste and generating electrical current, scales down. Microbial fuel cells operating on the same principle have been built and demonstrated at countertop scale, garden scale, and small homestead scale by researchers at universities and independent builders around the world. The biology doesn't require an industrial facility. It requires organic waste, the right microbes, electrodes, and the right conditions. All of those things exist at the household level. Small-scale microbial fuel cells running on kitchen food waste, garden compost, or diluted organic slurry currently produce in the range of milliwatts to low single-digit watts per square meter of electrode surface. Not enough to run a refrigerator, but enough to trickle charge a battery bank, power sensors and monitoring equipment, run low-draw LED lighting indefinitely, or supplement a larger off-grid system with a genuinely waste-powered baseline input. And the trajectory of this technology is important. Cambrian's founders have noted that across their NASA contracts, they gained critical experience iterating on materials and inoculation methods, validating that the biofilms the bacteria form on the electrodes are extraordinarily tough and resilient, far more stable than early researchers expected. That robustness is what makes this practical rather than theoretical. The bacteria colonize the electrode surface, form a biofilm, and keep working, continuously, with minimal oversight. Silver himself has described the broader trend this technology represents: extracting resources from waste, treating garbage as a potential source of value rather than a cost burden. That's very similar to how waste is viewed for space travel. Think about what that means at the household level. Your food scraps, your garden waste, your kitchen organic material right now that goes into a bin gets hauled away and becomes someone else's problem. In a microbial fuel cell system, that same material becomes your electricity, continuously. For as long as you keep feeding it, no panels, no wind, no fuel delivery, no generator maintenance, just biology doing what biology has done for 3.5 billion years, consuming organic material and moving electrons, except now those electrons flow through your system instead of into the atmosphere. The backyard version of this technology is not yet a plug-and-play product you can order and install in an afternoon. The commercial EcoVolt system is industrial scale. The small-scale DIY microbial fuel cell community is active, growing, and producing real results, but it requires some experimentation and iteration. What exists right now is the proof of concept, NASA-validated, commercially deployed, scientifically airtight, and a clear development trajectory toward accessible household-scale systems. The people building those systems are doing it now, in garages, in backyards, with electrode materials sourced online and bacteria cultivated from garden soil and compost. The knowledge base is public, the biology is not proprietary, and a technology that started with a NASA grant to figure out how to survive in space is working its way towards solving the same problem on Earth. Turning what you throw away into the power that runs your life. Subscribe to Lost Tech Vault. Next week, I'm covering exactly how small-scale microbial fuel cells are being built right now by the DIY energy community, the electrode materials, the organic inputs that produce the highest current density, and what a realistic backyard system can actually power today versus where this technology is heading in the next 5 years. You're going to want that one. See you next week.